let's have a look at this question. So here we are given a reaction in which we have to find the reagent which can convert a non-terminal alkyne into trans-alkene, right? Let's see. So we have CH3, C, triple bond C, CH3. We need a reagent which can convert it into trans-alkene, right? So what do we mean by trans-alkene here? Well, if both of the hydrogen atoms, they are on the opposite side of the double bond, right? That's when we call it as trans-alkene. Similarly, the both methyl groups are on the opposite side, right? So whenever two atoms or two groups of atoms are on the opposite side of the double bond, that's when we call that alkene as trans-alkene. And which reagent is able to convert a non-terminal alkyne into trans-alkene? Well, that is sodium in liquid ammonia. That is what? That is the Birch reduction, right? It is reduction. Why? Because hydrogen is being added to the triple bond to give us the alkene, right? Okay. Now let's have a look at the options that are given to us. Well, first option, we know that it's not correct. Why? Because this reagent is involved in the aromatization reaction of the alkanes, right? So that's why it's not correct. What about option B? Well, this is the reagent, which is Lindlar's reagent, which can convert a non-terminal alkyne into what? Into cis-alkene. So yes, even this is not the correct option. Option C is correct, right? What about option D? Well, we use sodium and dry ether in the Woods reaction in the conversion of alkyl halides to alkane. So even this reaction is not correct. So this option is not correct. So the correct option to this question is option C. Let's have a look at this question. So here we are given that we require 1.184 grams of NaOH for completion of the reaction. And we require 0.15 molar concentration of NaOH to complete this reaction. What do we have to find out? We have to find out the milliliter, right? The volume of this 0.15 molar aqueous solution that will be required to complete the reaction. Very, very easy question. You just have to know the formula of molarity, which is what? Well, that is number of moles per unit volume, and the volume has to be in what? It has to be in liters, right? We have been given molarity of the NaOH solution, which is 0.15. Number of moles. Well, we are not given number of moles. However, we are given the weight, right? And what do we know? We know that the number of moles, the formula of number of moles is what? Given weight divided by what? Molar mass, right? And what is, so given weight we know, which is 1.184 grams. What is molar mass of NaOH? Pretty easy, right? So it is 23 for sodium plus 16 for oxygen plus 1 for hydrogen, which comes out to be what? 40 grams per mole, right? So now we know our number of moles as well. And what do we have to find? We just have to find the volume. So volume in liters, okay? In liters will be equal to what? Number of moles, which we found out, 1.184 divided by 40 divided by molarity, right? So why divide? Because the 0.15, the molarity was in numerator in the LHS. So when we move it to RHS, it comes down in numerator, in the denominator. So it is 0.15. Let's calculate this. This is 1184 divided by 40. We have 1000 in the denominator, right? Because I removed the decimal from 1184, 1.184. And this becomes what? 100 upon 15. Okay, so this is 5. This comes out to be 2, right? Let's calculate this. 2 5s are 10, 9s are 18, 2 5 2s are 4. So 592, correct? So this is 5 3s are 15. So what do we have here? We have to divide 592 by 3. And we have 1000 in the denominator. So this is 3 1s are 3. Then it comes 29. So 9s are 27, 22, 7s are 21, 10.33, right? So this is also divided by 1000. right? So this is what? This is 0.197 liters. Correct? So this is the volume that will be required for the complete reaction. However, we are given our options of volume in milliliter, right? So what have we calculated? We have calculated 0.197 liters, right? So what would it come out to be? It would be, we'll multiply it by 1000 to get our volume in milliliters, which will be approximate 197 milliliter. Okay, so which option does it match? It matches option A, which is our correct option. Let's have a look at this question. So here we are given 16 gram of oxygen gas, which expands at STP to occupy double of its original volume, and we have to find out the work done. Okay, so what is 16 grams of oxygen? Well, it is what? It is 0.5 mole of oxygen. Correct? Why? Well, oxygen has the molar mass of 32 grams per mole. So it cancels out 1 by 2, which is 0.5, right? So we know that 1 mole of gas at STP occupies 22.4 liters of volume, right? So 0.5 mole will occupy how much? It will occupy 11.2 liters. This will be our V1 volume initially with the before the expansion, right? And when it expands, it occupies double of its volume. That means V2 will be 22.4 liters. Right. Now, since expansion is happening at STP, right, this is a typical case of what? Expansion at constant external pressure, right? And for that, the formula of work is minus P external V2 minus V1, right? So what is the value of P external? Well, at STP, we'll take it as 1 atmosphere minus 1 into V2 is what? 22.4 liters. V1 is 11.2 liters. Comes out to be minus 11.2 liter atmosphere, right? Let's check out the options. Okay. Oh, wow. So the options are not in liter atmosphere. The options are in calories, or you can see kilocalories here. Okay. So what do we do now? Well, it's very obvious that for the R value of 0.0821, you got work in liter atmosphere, that is minus 11.2, right? However, if you want the work in calories, what do? We take the value of R as 2, right? Let's calculate. So it will be minus 11.2 divided by 0.0821 multiplied by 2. Okay, this comes out to be what? Minus 11.2 divided by 10. Let's approximate 0.0821 as 0.082. Okay, so this will be multiplied by 1000 divided by 82 into 2. So this is 41. 1 0 cancels out. So this comes out to be approximately minus 11.112 divided by 41 into 100. Right? So what do we have to do? We just have to divide 112 by 41. Let's do that. Pretty easy. 41 2s are 82. This is 30. Decimal 300. 7s are 287. This will be 3. 130. Right? So this is 3 and this is 123. I think we are good here. So we get minus 273 into 2.73 into 100 comes out to be approximate value as minus 273 calories, right? These are calories. Okay. Why? Because the value of R is 2 what? Is 2 calories per Kelvin per mole, right? Not kilocalories, calories. Okay. So let's see, what do we have? We have minus 273, approximate value is minus 273 calories. Let's see which option does it match. Well, it matches our option C, which is the correct option here. Let's have a look at this question. So here we are given 3 compounds and we have to find the decreasing order of their pKa values. And you know that higher the acidic strength, lower will be the pKa value. Okay. So while comparing the acidic strength, first thing that you have to do is you have to find out their conjugate bases. Okay, let's do that first then. So we have CH, triple bond CH. The conjugate base would be what? We'll abstract one H plus ions, right? So this ethyne has two acidic hydrogens and both are equivalent in nature. So what we will have? CH, triple bond C minus. This is the conjugate base of compound 1. Okay. Now, what is the second compound? Well, we have 1, 2, 3, 4, 5, 6, 7 carbon atoms in the ring. Let's see what would be the conjugate base of this compound. Well, it has two acidic hydrogens, right, which are equivalent in nature. So what we'll do, we'll abstract one of these acidic hydrogens, right, and we will get the conjugate base, negative sign on this carbon atom. So this is the conjugate base of compound 2. Next, what do we have? We have benzenoid ring and we have a 5-membered ring as well attached to it. Okay, so we have benzene and a 5-membered ring attached, and we have a double bond here, right? So even this molecule has two equivalent acidic hydrogens. So we'll remove one of them to get our conjugate base. Okay, so here we'll have a 5-membered ring. Okay, so these are the conjugate bases of these 3 compounds given to us. Now we'll compare the stability of these 3 compounds. Higher the stability of conjugate base, more acidic will be the compound. Okay, so first let's see the stability of the first conjugate, the conjugate base of the first compound. Well, the negative charge is on an sp hybridized carbon, right? So the S character is 50%. So this negative charge is fairly stabilized. Okay. Now what about the conjugate base of compound 2? Well, the conjugate base of compound 2 is actually anti-aromatic. How? Let's see. It is cyclic in nature. Yes. It's planar. Why? Well, it is planar. This carbon has 3 sigma bonds and this negative charge is being delocalized over the molecule, right? So how many pi electrons are being delocalized? 8 pi electrons are being delocalized and all the carbon atoms are sp2 hybridized, even this carbon ion. How? Well, the 3 hybridized orbitals are planar. And since the negative charge is being delocalized, it has to be in what? It has to be in a pure orbital which will be perpendicular to this plane, right? So that's why this carbon atom is sp2 hybridized, which makes the whole molecule planar. And 8 pi electrons are being delocalized in this molecule, right? Which makes it what? Which makes it anti-aromatic. 4n pi electrons, right? If you put n as 2, you get 8. And this makes it anti-aromatic and hence its stability decreases a lot. Okay, what about the conjugate base in compound 3? Well, it is cyclic. Yes, it is planar as well. How? Well, the same scenario. This negative charge is being delocalized, right? And how many electrons are being delocalized in this molecule? Well, there are total, 4 pi bonds, that means 8 pi electrons, and we have 1 negative charge as well, that means 10 pi electrons, right? If we would put, so for Huckel rule, it has to follow 4n plus 2 pi electrons. If we put the value of n as 2, what do we get? We get 10. So it follows Huckel rule as well. It is cyclic, it is planar, that makes it aromatic. Hence, the conjugate base of compound 3 is highly stable, right? So if we want to compare the stability of conjugate bases, we will say that the conjugate base of compound 3 is highly stable, right? More stable as compared to conjugate base of compound 1, followed by conjugate base of compound 2, right? Since the conjugate base of compound 3 is most stable, that means it is most acidic. And since conjugate base of compound 2 is least stable, that means it's least acidic, right? So if we are talking about acidic strength, I would say that compound 3 is most acidic, followed by compound 1 and followed by compound 2. However, we know that the pKa value of most acidic compound will be smaller, right? So that means pKa value of compound 3 will be smaller as compared to pKa value of compound 1, which will be smaller as compared to pKa value of compound 2, right? And this is what we wanted to find out. We wanted to find out the decreasing order of the pKa values of the 3 compounds. So pKa value of compound 2 will be highest, followed by compound 1, followed by compound 2. Let's see which option does it match. 2 highest, followed by 1, followed by 3. Well, that is option B, which is our correct option. Let's have a look at this question here. So here we are given an aqueous solution of barium nitrate, right? And the concentration of nitrate ions in that aqueous solution is 0.08 molar. And what do we have to find? We have to find the concentration of this aqueous solution. Okay, so if we have barium nitrate, BaNO3 whole twice, right? If we have the salt and if we put it in aqueous solution, right? So what would happen? Well, in aqueous solution, barium nitrate will completely dissociate to give us barium ions plus nitrate ions, right? This is the balance equation for this. Correct. So what do we know from this? We know that if we have 1 mole of barium nitrate, then if we add 1 mole of barium nitrate in that aqueous solution, we'll get what? We'll get 1 mole of barium ions and we'll get 2 moles of nitrate ions. That's what is given to us here, right? And what we have been given is, we have been given the concentration of nitrate ions as 0.08 molar. Okay, so let's assume that the volume of the solution is what? 1 liter. If the volume is 1 liter and concentration of nitrate ions is given to us as what? 0.08 molar. What does that mean? So 0.08. So that would mean what? That would mean 0.08 number of moles. How? It's very easy actually. So if you have 0.08, molarity is 0.08, right? Which is equal to what? Number of moles divided by volume in liter. And if you take volume as 1 liter, right? So what do we get? The number of moles as 0.08. Okay. Okay. So now what do we know? We have volume of aqueous solution as 1 liter, right? And we have 0.08 number of moles of nitrate ions in that aqueous solution, right? Now what do we need to do? We'll backtrack, right? So if we have 0.08 number of moles of nitrate ions, that what does that mean? That means that initially we would have 0.04 moles of barium nitrate, right? And it would have dissociated to give what? To give 0.04 moles of barium ions, and we would have got 0.08 moles of nitrate ions. Correct? This would have been the equation. These would have been the number, right? And since volume we have assumed as 1 liter, what we can say? We can say that the concentration of that barium nitrate aqueous solution would be what? 0.04 divided by 1, which is 0.04 molar. Right? Let's check out the options. Okay. So it says 0.04 normal. Okay. 0.16 molar. No, it is 0.04 molar. Right? 0.08 normal. Okay, we have not checked the normality. We still have to do that. Option D says 0.8 molar of nitrate ions. Okay, this might seem correct, but we have to find out what? We have to find out the concentration of the solution, not the nitrate ions, right? So that's why option D is also not correct. Now option A and C are talking about normality of barium nitrate. However, we have only calculate molarity, right? So let's calculate normality as well. What do we know? We know that normality is equal to molarity into N factor, right? And here we have to find the N factor of a salt. And for a salt, the N factor is equal to what? It is equal to total cationic or total anionic charge. So here we can see what? We can see that the total cationic or anionic charge is 2, right? So molarity will be normality will be molarity into 2. That becomes 0.04 into 2. That becomes 0.08 normal solution, right? 0.08 normal barium nitrate solution. Which option does it match now? Well, it matches our option C, which is the correct option here.